Makako has impressively remarked on the remarkable contributions he has made in the field of material science, stating that the James Webb Space Telescope has uncovered 6 massive galaxies, which experts once believed couldn't exist. These discoveries have significant potential to open new perspectives on how we interpret the cosmos. The simplicity of these findings is both captivating and humbling, as they challenge current theories regarding the creation and evolution of galaxies. It is essential to pay attention to these revelations, and Makako's acknowledgement of their importance highlights the significance of these discoveries. As a physicist with dual American and Japanese heritage, Makako is regarded as an authority in both traditional material science and quantum mechanics, distinguishing himself from more conventional and cautious researchers. He has embraced the extraordinary possibilities presented by the James Webb Space Telescope mission. His eagerness to explore new findings and share them with the public reflects his dedication to advancing our understanding of the universe. We are grateful that this distinguished expert has decided to end his silence and openly discuss these undeniable revelations. The powerful, clear voice of this extraordinary physicist is evident in his remarks on the discoveries made by the James Webb Space Telescope, suggesting that this breakthrough has rekindled his interest. Join us as we explore the implications of Makako's transparency regarding these 6 colossal galaxies. Makaku is a distinguished figure who has consistently shown an ability to entertain novel theories throughout his life. He has displayed a sensitivity to ideas that challenge conventional wisdom, understanding that while Einstein's theories of relativity and Newton's laws are foundational, they fall short in fully explaining the intricate design of the universe. Makako believes that the discoveries made by the new telescope could propel the field of cosmology, though many of his colleagues are still reluctant to accept this viewpoint. This reluctance has stirred skepticism among Big Bang theorists and critics of quantum mechanics. Nevertheless, this response amuses Makaku, as the James Webb Space Telescope has revealed 6 enormous galaxies dating back to the very earliest epochs of the universe. Each of these enormous systems contains more stars than our Milky Way, despite forming merely 200 to 700 million years after the Big Bang. The group of astronomers who made this discovery have dubbed these magnificent galaxies universe breakers. If their existence is confirmed, they would dramatically alter our understanding of the cosmos. The results of these findings suggest that the early universe was far more diverse and complex than previously believed. The theory of the universe's origins tells us that the cosmos was turbulent after the Big Bang, with the first solid objects taking a long time to form and even longer for them to gain sufficient density and emit light. The development of complex structures, like galaxies, was assumed to have occurred much later. Some of the recently discovered giant galaxies surpass the Milky Way in size, and their immense brightness indicates that they may have been forming new stars at an extraordinary rate. Unlike our galaxy, which produces stars intermittently, the exact moment these structures first emerged remains unclear. But one thing is evident. Initially, there may have been only isolated stars or small groups of stars that eventually coalesced into larger structures over time. Smaller systems supported the formation of larger, more substantial structures. Previously, it was believed that such enormous and intricate galaxies couldn't have existed at such an early stage, raising the question of whether the universe is much older than previously thought or if these massive systems formed far earlier than expected. This scenario challenges conventional science, which still struggles to reconcile this model. Certain branches of physics have outright dismissed these findings, questioning the accuracy of age estimates. Makako acknowledges this and responds by saying that many outdated theories persist due to the influence of well-established experts. These theories were scientifically disproven when key research revealed their flaws. The truth in science, particularly in physics, lies in the work of experimentalists who continually refine hypotheses to ensure they remain on track. He further explained that here on Earth, we possess very little knowledge about the true origins of the universe. This statement underscores the importance of continuous testing, revising, and reaffirming ideas within the scientific process. The theory of the universe's origins was first articulated in 1927 based on observations of the cosmos expansion. This data led to the conclusion that the universe began as a single infinitely dense point and has been expanding ever since. At that time, it was difficult for both the public and scientists to imagine a universe with a beginning and an end. The possibility of an eternal universe was beyond human comprehension, and even today, researchers still struggle to fully grasp it. However, it remains essential to entertain such possibilities, even if the new discoveries do not align with what experts have accepted for centuries. As for the theory of the universe's beginnings, science has demonstrated numerous times that reconsideration and openness to bold ideas are vital to the scientific process. For example, when Einstein was younger, it was once believed that stars and planets were fixed in place within the universe, occupying specific regions. Today, however, we understand that everything in the universe is in motion. Planets orbit stars. Stars move within galaxies at speeds of several kilometers per second, and entire galaxies move swiftly through the cosmos, whose ultimate fate remains unpredictable. This remarkable understanding challenges long-held beliefs and emphasizes the necessity for ongoing inquiry and flexibility in our scientific thinking. Today, scientists are tasked with identifying anomalies and ensuring that theories are not lacking until they have been thoroughly tested or validated by empirical data. The idea of the Big Bang emerged from the observation that galaxies are receding from one another, with the distance between them correlating with their separation from Earth. This theory, known as Hubble's law, suggested that the universe has been expanding over time. Factors such as cosmic microwave background radiation and the redshift of light from distant galaxies, along with other cosmological patterns, seem to support this theory. However, it is crucial to remember that in the past, people believed the Earth was flat and that the Sun revolved around it, also citing observational evidence to support their beliefs. It wasn't until new events or technological advancements provided a clearer picture that these ideas were debunked. We are currently in a similar situation. Scientists had predicted that the James Webb Space Telescope would confirm questions related to the theory of the universe's origins. However, the telescope's findings have challenged these expectations by revealing 6 massive galaxies that defy previous notions. This demonstrates that science is constantly evolving, and researchers must remain open to new discoveries and re-evaluate existing theories based on the evidence at hand. The unexpected findings have tested our current understanding and prompted a reassessment of long-established cosmological theories. Researchers employ redshift as a tool to gauge various measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the shift in the wavelength of light as the light source and observer move relative to one another. To illustrate, imagine standing still and hearing a car approach. As the car gets closer, the sound grows louder, but as it passes by or moves away, the sound diminishes. The same principle applies to light. When a light source like a distant star approaches us, the light shifts toward the blue end of the spectrum, while if it moves away, it shifts toward the red end. This phenomenon is called redshift, and physicists have converted redshift values into percentages and distances to measure the universe's expansion. However, it's essential to recognize that even small errors in these measurements can lead to significant consequences. The previous methods of evaluating redshift are now being re-examined. The latest discoveries regarding our universe require careful consideration to determine whether they are the result of redshift errors or if some scientists are simply ignoring the new facts. This question calls for a thorough review of the data and methodologies used in these investigations. The continuous process of assessing and reassessing measurement techniques underscores the growing understanding of the value of continuous inquiry.